Hi, my name is Ian Ibbotson and Elliot has asked me to give you a brief presentation on the architecture of a global scale alert hub. I've been working with Elliot for, I don't know, maybe just over a year now on various aspects of this. I'm sorry I can't be with you in person, and being a distance away, it seems sensible to record this presentation rather than try and give it over Skype. If I can be there in person, I will, but if I can't, this is our fallback position. So, how did we get here? Elliot originally asked me to contribute because we worked together a long time ago, back in the days of Oracle Spatial Search, trying to combine Oracle Spatial Search and its full text searching, back in the very early days of quad tree indexing. Since then, I've worked a lot in text search and spatial search, and Elliot had some issues with matching profiles against alerts. He asked me if I could lend a hand, see what we could come up with. In the intervening time, I've been working a lot with Elasticsearch as well, and Elasticsearch has some really great service-oriented facilities for building these kinds of searching solutions, so we thought we'd have a go with that as a way to provide a solution. And also been working in microservice and serverless architectures, which is something which appealed because of their ability to scale very quickly in response to high loadings. What we really wanted then was a service which, given an alert, could match any subscriptions which were defined by a polygon. So we had an alert with a polygon in, or a circle, and we wanted to define our alerts in terms of polygons and then return a list of any overlapping shapes so that we could say, okay, this alert applies to these 5 subscriptions, for example. Elliot very kindly supplied me with a list of alerts. You can see this URL here, the alert hub subscription/JSON. I think it currently contains just shy of 400 subscriptions that cover the globe, major cities, major areas. So we ploughed ahead and built a version 1 system based on Elasticsearch, and the piece that I was looking after specifically was the ability to give a bound polygon to the service and retrieve back a list of subscriptions. And that worked quite well. Elasticsearch's spatial matching is really efficient. Once it's warmed up, it'll return at the millisecond level. Very efficient. Loading the subscriptions takes a little while. It takes maybe a minute to load the 400 subscriptions. Some of them have got quite high precision polygons, so building the indexes takes quite a while. But generally speaking, that works okay. Those of you who might have worked with Elasticsearch would normally see a search string which looks like this. So we have a base URL for Elasticsearch, and then an index name, and then a service. So here we've got the search service with a query of Sheffield, and that would return me some documents. Searching for polygons is a little bit more difficult because we want to be able to provide quite complicated shapes and quite a lot of structure. So here's an example of doing a spatial search where instead of using a URL query, we're posting a JSON document to the search interface. So you can see the same structure, Elasticsearch base, index name, and the search verb, but then we're submitting this JSON document to describe our search instead. And in this case, we're using a filter query for a circle with a radius, with a center here and a radius of 20.8 kilometers. And we're looking for any shape which intersects this. And this worked really well. I don't believe that the Elasticsearch part of the process was a particular bottleneck. And just to recap, this is very much my recollection of the architecture at the time. This is for historical purposes, it's not how it is now. What we had was the internet filled with feeds. Then we had some Python code which was basically polling the feeds. We used a key store, a key value store, to be able to store IDs, to be able to do deduplication and make sure we weren't emitting duplicate events. When we detected a new item, we called a different Lambda function. So this was in Python. Over here we've got a JavaScript function which was responding to new events. That was then talking to the Elasticsearch service that I've just described, finding a list of matching subscriptions, passing that back to this handler, which was then responsible for publishing in S3. And this is quite nice. We go from a set of static feeds on the internet here to a set of static feeds which are basically our subscription feeds over here. And the nice thing about S3 as a venue for publishing the feeds, of course, is that you can rely on the infrastructure of the internet to copy those files around and to cache them appropriately and expire them when they change. And static RSS feeds don't need compute infrastructure to maintain them, basically. Once you've minted them, you can replicate them wherever you like, and that's quite efficient. Just to do a little retrospective of that and why we felt we needed to evolve the situation a little bit. This piece, polling all the feeds, the 400 odd, 400? There are a few feeds out there. It's incredibly difficult to get right. Different servers will implement semantics subtly differently. Some will support HTTP head, so it's very easy to find out if a document's changed or not. Some will automatically respond with the current system time as the date last modified, so you can't tell by looking at the last modified date if anything's changed, and you have to do something more invasive with the file, maybe hash summit. And so this area was quite high friction, and another problem was it's quite bursty, so sometimes you will find a feed with 40 new alerts in it, and it was difficult to get this running smoothly. I think is not unfair, and smoothly and reliably. When there are problems, because this was running in a Lambda environment, it's quite high friction trying to decode and debug what's gone wrong, and it feels a little bit like a closed box in some ways. So if I wanted to feed back to the owner of a feed that their RSS certificates have expired, that usually would involve trawling through the logs and the CloudWatch logs to try and find the appropriate bit of logging. What we started to feel was that we'd like to open this process up a little bit more and give ourselves more hooks to intercept error cases and report back on them. Having said that, the event handling seemed to work okay, except for when it didn't, and sometimes we would see quite large gaps in the invocation of a Lambda function, and we weren't really sure why that was. And again, implementing some meta-logging or some analytics on top of that turned out to be really important, because we want to know when there are unexpected large gaps in processing time and where those gaps are appearing. The polyglot nature of this, the fact that we've got some Python Lambda here and the JavaScript Lambda, that's cool. That really is nice. Really like that part of the service, and that worked incredibly well. Everybody worked in a tooling that they were comfortable with. Everything did work together. Again, debugging over here, we ended up with a lot of systemed outs in the JavaScript, or console.logs rather. And that was our go-to method of debugging those, which it worked okay, but it didn't feel very 21st century. This all worked okay, I think. We had to devise some mechanisms for updating the subscription matching database, but overall that worked okay. And the publishing to S3 occasionally became a bottleneck where we'd see things queued up, and in fairness, we've only just started to understand what the nature of those bottlenecks were and what was going wrong at that stage. I'll probably talk about that towards the end of the presentation. So that was the architecture that we had, and that worked okay, except for when it didn't. And when it didn't, finding out why it wasn't working okay was slightly painful. And that's a problem. So, to kind of conclude the retrospective, the lessons that we learned, I think, are that if you aren't in complete control of all your feeder services, the ability to report on error cases and problems from your feeding services is really crucial, and it's difficult if you're in a high friction environment to deal with that, because of course what would happen is Elliot would call me and say, we're not getting alerts through from this source, and I'd be really busy, and I'd say, okay, well, I'm going to have to find some time to pull the logs and grep through them and find the right bit. Can you get them to publish another alert so that I can trace one going through the system? It's something which we'll come on to. The ability to isolate your system completely and just focus on one provider was something that back then really I wanted to be able to do. I wanted to turn everything off apart from that one feed that was giving us problems. And that's not always ideal, because sometimes problems are an interaction of all the feeds together, and it's the loading of the whole thing which causes problems. But when you've got a problem with an individual feed, switching off everything else on your test server turns out to be a really useful thing to do, so we can just really focus on those problem feeds. And really that's the lesson, I think. Whilst we got something that worked end to end, we didn't have the ability to do deep diagnostics of specific error cases. And that was something that I felt we needed to address, because I needed to be able to more quickly respond and more efficiently respond to error reports, in essence, and backlogs. Why are things not coming through? What we did then was, pardon me, my phone is ringing. What we did then was to evolve the architecture, and we've come up with 3 components, really 2. We have a component called feed facade, where we just isolate all the code to do with pulling RSS and Atom feeds, and indeed any other kind of feed. If we wanted to write some screen scrapers, we could put that code in there. And feed facade is completely dumb when it comes to CAP. It doesn't know anything about CAP. All it knows is there are some protocols that enumerate changes, and it can detect new entries and broadcast an event. So it'll say there's a new Atom item or a new RSS item, but it doesn't know anything about the contents of that. We have a second component called CAP Collator, which really does know about the semantics of CAP, and it listens for those Atom and RSS events, looks at the individual items to work out if it thinks that that alert is about a CAP event, and it does that a number of different ways. It'll look at the event type. If it can't work it out from that, it will go and fetch the URL and see if it has a HTTP header, which will give us an idea about the content type if it's application CAP. If that doesn't work and it's XML, it'll try and parse the document and see whether or not it's a CAP alert and whether it has all the elements that we need. So the interaction between feed facade and CAP Collator gives us quite a nice separation of concerns. Feed facade only concerns itself with the knotty problem of monitoring a load of external Atom or RSS feeds or web pages that you want to parse yourself to look for new entries and detect new entries, deduplicate those, and make sure that it's not emitting duplicate events. CAP Collator subscribes to that feed and then acts accordingly. So we've tidied things up. There's also a DevOps project here. If you wanted to run one of the things I'm about to show you, then you can just grab, there's actually a Docker container on Docker Hub that you can just grab and run, and you'll get a full system. Or you could run the developer environment and then you could manually run the services on top of that. So there's a DevOps project where we just bundle everything up. And in fact, the way we deploy to the live server is by deploying the Docker Hub project. So we'll push a new Docker image and then we'll pull that down to AWS and run it there. To talk to you a little bit about Feed Facade then. Feed Facade is our component for monitoring remote RSS and Atom feeds and anything else that we want to be able to poll, basically, to turn those pull-based resources into push-based events. So this is where we isolate all the logic to do with polling remote sources. It uses PostgreSQL to maintain a database of remote feeds. We can run as many copies of Feed Facade as we want, because in actual fact the database has been used to control that. So each feed has a poll interval which can be set to any number of seconds, and as each feed comes live or becomes ready for polling, it's pulled off the queue and updated so that only one instance of feed facade is ever going to poll that thing. It does the polling and it updates the database. So we could have 5 copies of feed facade running, all looking for feeds to poll and grabbing them. We currently only run 1 instance of feed facade on quite a lightweight AWS box. It's a 2-core with 8 gig of memory, but it runs okay. But if we wanted to scale this up and get faster responses, then that would be the thing to do. We could scale it out. As I said, this is basically just an abstraction over RSS and Atom that turns those pull-based formats into a reactive stream of events. The messaging substrate is agnostic. We've decided to use RabbitMQ because that's something that we know about, but actually Kafka would be an equally good choice. In fact, RabbitMQ is quite nice. We exploit some of the topic publishing with Rabbit, but there'd be no reason why we couldn't insert other messaging substrates in there. Rabbit has some quite nice web-based eventing tools that we can use to integrate web services, so there's some fun there. And this is a screenshot of feed facade, but what I think I'll do is just go here. So this is feed facade running on the test server. It's got what, 11 pages here, and I think there are. I don't know. I thought there were 10 per page, but there's definitely more than 10 there. What we've got here then is a list of all the feeds currently running. All the feeds have a code. So the first on the list is AIDMAEN. The toggle enabled allows us to switch individual feeds off and on. Over here on the admin menu, you can see I've got to disable all. So this is quite useful for the test server. What I can do is shut off all the feeds and then just turn one of them back on. And back at the start I was saying it's nice to be able to isolate your system so you can just look at one feed. This is the way that we can do that. I can register new feeds, all those good things. Over here we've got a histogram, and this is the last 24 hours. And you can see we have an error count row. So this tells me where we've attempted to pull the feed and we've had an error back. And you can see this feed is being extremely well behaved. We've got a success count here, and basically it's usually 30 per hour. This feed we're checking once every 120 seconds. And you can see just occasionally, for whatever reason, we only managed to get 29 checks in an hour. You can see that right now, in the current hour, 9, we've only done 23, but that's because it's close to the end of the hour. So that's our success count, and then on the bottom we've got new entries. So this is telling us this is how many new entries we've detected in that particular hour, and you can see on this feed there are none. The feed status, green tick means it's working okay as far as we can tell. A red exclamation mark means things aren't okay, so you can see this feed is just erroring constantly. There are no successes and no new items, and you can see over on the right hand side that the problem here is an SSL handshake violation. So this feed is currently down and not operating. You can see this feed here, we've got some successes, we've got no errors, but this is quite a busy feed. So you can see this feed has given us 11 new events in this hour. And if I click on the feed, we can see the actual XML fragment. So you can see, if I can find it, the XML fragment that begins items. So what we're doing here is we're yanking the item element from the XML source document. The way that the system works internally is by passing JSON around, actually. So we convert the XML into a JSON record because it's a little bit more convenient, especially for working with Elasticsearch. So what we've got then for this feed is the XML, the element, and then side by side the JSON that we're actually going to pass around, just to make sure that we can marry the two things up and make sure I'm not destroying any intentionality. And so that's a way that feed facade works basically, and it's completely dumb. It doesn't know anything about the contents of the items. All it knows is that there are items in Atom feeds and RSS feeds, and it'll convert them to an event and emit that event. I don't think there's much more to say. You can see, here's a different example, JavaNet socket timeout. So for some reason we're having trouble connecting to this particular feed. It'll hang on to the last error. So if there's one error and then everything returns to normal, we can go back and see what was happening. I'll probably talk at the end about enhancements we'd like to make to Feed Facade. Some things I'd like to be able to register either email addresses or Slack handles or SMS numbers, so that if you're responsible for a feed, we can alert you if we're getting 404s or other messages. Similarly for invalid cap, but that's a slightly different concern. Yeah, but I'd like to up the error alerting and provide people with a way to alert them that we think their cap feed is currently not behaving as it should. Yeah, so that's Feed Facade. Cap Collator, on the other hand, is our very cap-specific thing. Cap Collator listens out for events which are published on a topic by Feed Facade. Cap Collator listens for new Atom or RSS event and says, okay, let me see if this item is in fact a cap event. So sometimes in feeds we see events which are not cap. So Cap Collator, the first thing it does is to filter out those events which aren't cap and ignore them. But if they are, then it'll say, okay, I think I've got a cap event here. It'll fetch the actual XML document, which is the cap alert, and then try and parse it to see whether or not it parses. If it parses, it'll then do some other validation. So we want to make sure that the polygon is actually a closed loop, for example, or that the polygon doesn't cross itself. We can do all that error checking. If we think we've got valid cap, then Cap Collator will itself issue a topic which is valid cap event. It then subscribes to that event itself, and that's when it'll do the subscription matching. So then we'll go back to our Elasticsearch routine and we'll try and figure out which subscriptions match an alert. We'll then publish an event for all the subscriptions that matched, and we'll do some event handling based on that. And right now the event handling is to dump the alert into our own Elasticsearch index of events or alerts. So we main two Elasticsearch collections actually now. One is the subscriptions database, but we also maintain a proper index of alerts, which there's a configuration switch. So we can either just build up a historic view of all alerts over time, or we can remove those that have expired. I'll show you that in a little while. The other thing that we do is we have a static RSS updater, which is very much like the old S3 publication mechanism, and that will publish to a static S3 bucket and maintain an RSS feed. The software can break, it can go away completely, but the RSS feed will still be there, still be propagated around the AWS network, which is really cool. So as a mechanism for making sure that the service, you can at least always read the feeds, that's quite cool. The net effect then is a really loosely coupled service that separates out the problem of fetching RSS and Atom feeds and other mechanisms of publishing from doing subscription matching and publishing subscription-based RSS feeds. This is Cap Collator, but again what I'll do is I'll try and switch to the live service. Here we can see the list of subscriptions, and what I can do is if I go to the unfiltered subscription, this is subtly different to, I know you'll have seen almost certainly, if I can find it, Elliot's map. This is consuming the static RSS feeds to draw all the current alerts on a map of the world. This is slightly different. This is searching our local Elasticsearch index of alerts rather than a static RSS feed. Not better or worse. This is quite useful for me though, because the alerts which get indexed here have a lot more debugging information attached to them. So you can see as an alert works its way through the Cap Collator system, we log a number of events. So when Cap Collator gets notified of an Atom event, it was an Atom feed in this case, we log the time here. Once we've worked out that we really think it is a CAP alert, we do a HTTP GET of the actual alert XML, and that time is logged here. So you can see that we were notified that Feed Facade had detected a new atom entry at 09:32:47 and 0.437 milliseconds, and the HTTP GET had completed at 09:32:47, and actually barely 50 milliseconds later. That's incredibly good. Normally it takes half a second or so for us to complete the HTTP GET. Obviously that's quite internet dependent and host server dependent. Once we've got the raw XML, we have to parse that into a DOM tree so that we can interrogate it. So the parse was completed 250 milliseconds later, basically. So that's quite good as well. And then we detected that it really was valid CAP and that we were able to parse it, and we'd emitted a CAP event at 09:32:48. And I've actually got this is quite a good alert, actually. I have to say they're not usually quite this quick. I don't want to misrepresent our processing speeds. There we go. Just to prove my point, spatial processing was complete at 09:42, so this was 10 seconds later. Not quite sure why there was a delay there. So we emitted the CAP event, and then what we did was we said, okay, for this event, for this CAP feed, please do a spatial search to find me all the overlapping subscriptions, and in actual fact, the subscriptions which matched this alert. So this was the XML. Tell you what, why don't I just quickly paste that into a browser window. Okay, so you can see that this alert consists of quite a few polygons in quite a lot of detail. So this is probably why this one took 10 seconds to process. So what's happened is we've worked it out and we've done a spatial search for each of those polygons to find all the alerts, all the subscriptions which will overlap all of those polygons, and that list has turned out to be this list of feeds here. So unfiltered, which is this feed, and that's basically the world. Official high priority public, official public, country RU city SWIC 969, and then we have the country Russia. So you can see that's essentially how this is working. We've got an alert identifier. This is all Capculator does, basically. It looks for RSS and atom events, validates them, does spatial searches for all the polygons that we find in an alert, matches them with subscriptions, records the alert in its own alerts database, but then also updates a static feed. So each of these feeds will have been rewritten with this alert in, and what I can do is, this is obviously the static alert feed for unfiltered, and this is it as XML. Can I find wind? Let's have a look. What was this? Headline was wind on its own. Okay, you don't want to see me going through this file, but if I go through the file far enough, I should be able to find that alert for wind. Here's the feed for the unfiltered alerts, and you can see we've got an item. We insert some Capculator special properties in. These are really so that we can figure out how we're doing on timings, so that Elliot has some cute scripts which do timings. We also say this is the ID of the source feed where we harvested this alert from originally. Obviously alerts can come from multiple feeds, so this is the one where we detected the alert. Yeah, and that's what that does. Don't know if there's anything else to show you with that. We've been playing with some facilities for using HTTP location, so you can see the alerts near you. That's quite good fun. Yeah. If I log in on the admin menu, oh yeah. if Elliot produces a new list of JSON alerts, we can bulk load those alerts using this interface. That's quite handy. Yeah, that's Capculator. Not terribly exciting. Okay. The DevOps project then, as I said, basically gives us a Docker container where we can bundle all these components up and just install them on the machine. The demo server that we were just accessing there, in essence, it's a bare bones Ubuntu box with Docker Compose and Docker installed on it, and we just fetch the Docker image for the system and do Docker Compose up. And that gives us a working system, which is a really nice way of deploying to a test server, and when we're happy that test works, just promoting that build to live, basically. So we've got some nice infrastructure. That all as a picture then. We have our Postgres database. We have many feed facade instances running. In practice, only one on quite a small server, but in theory, there's nothing to stop us running as many as we want. Postgres, we have a single Postgres install, which is basically coordinating the activity of all these things. Each one will pull a feed off the queue of things that are pending, process it, and then release it back. So that's what Postgres is doing. That's how it's organizing that. Basically acting like a mutual exclusion lock. When feed facade detects new items, it emits an event on a topic. Capculator subscribes to that topic, but there's no reason why anything else couldn't subscribe to those events as well. When Capculator works out that it's got a valid cap event, it itself will emit an event on a different topic, a different queue, saying, hey, there's been a valid cap event here. The handle cap code will then fire because it subscribes to that particular queue. Again, anything else could subscribe to that queue if we wanted to have some kind of historic cap logger that wrote files to an archive and just logged everything. We could write that as a different thing that was listening to that queue. The cap handler will talk to Elasticsearch to find any matching subscriptions, and itself will publish events for all the subscriptions that match. So the unfiltered subscription will match, and country and city specific subscriptions will match. We get one event for each of those, which means that if another application wanted to subscribe only to unfiltered alerts, or only to alerts for a specific city, or only to high wind alerts, or only to missing child alerts, we could have different listeners here. When we emit an event that says we matched a subscription, there's a different handler which listens to that event, and again, other handlers might listen. This one in particular updates our alerts index in the Elasticsearch, and it also writes to S3, so it writes the static feed. So all these things are capable of running on different boxes, and we can scale them out. We can run as many copies as we want, and here, where we're pulling messages off the queue, we can constrain it so that only one of the Capculators pulls each of these messages off that queue. So that works quite well. It means that we won't get duplicate entries in S3, but we can scale out the collator. So that's quite good fun. Recent problems, recent issues. I'm still working through getting all the date time formats right. Elliot has a list for me of places I need to fix that, but if you spot them, feel free to create GitHub issues and pester me if it's causing you problems. We spotted some problems with the S3 writing. Sometimes a feed is related to a very specific geospatial area, and it'll get 40 alerts dumped into it, which means we end up writing a file 40 times and publishing it to S3. Clearly that's crazy. So what we did was we wrote a delayed writer, and if we think we need to update a particular alert feed, for example unfiltered, we will queue up that write but not write it immediately, and if there's another write to that file, we will update our queue instead and wait a little bit longer. Basically it's 2 seconds, so we try, before we write, we wait 2 seconds to see if anybody else wants to write to it, and 2 seconds is usually about long enough for the backlog to clear, in fact, and then once nobody's writing to it, we'll write the delayed update, and that improved the situation radically, I have to say. So instead of writing an update to the unfiltered feed 40 times, we might write only once or twice, but write a batch of 10 updates. That's improved the situation drastically. In fact, the way that this works is the static files are held locally, and then we just push the local file up to S3. So we update the local file, and then we push an update to S3. So there's been quite a lot of optimization around the S3 file writer. That's working quite well. We still get occasional lag spikes. The example earlier on in the presentation of the alert that had maybe 10 polygons in it, some of them quite detailed, that accounts for some of the spikes, but I think we've still got one or two interesting scenarios out there. Maybe a source is slow to respond, maybe there's something internally. So we're constantly evolving the logging and the instrumentation to try and figure out where things are going wrong, or where the delays are and where the bottlenecks are. Future developments, I think we're going to have a go with Kafka. It should be really easy to pull RabbitMQ out and put Kafka in, maybe have it as a configuration option. The really nice thing about Kafka is we can replay the event stream. So we could write a new service and then just replay the entire event stream, and it's as though, you know, it was there from day zero. That'd be quite an interesting thing to try. I suspect that we are going to need in this infrastructure an event publishing application. The real reason I want that is to try and be able to mock up servers for our testing. I'd like to have a more reproducible testing environment. That's quite tricky to do when you're drinking from the fire hose of feeds. So I'd like to have an event publishing mechanism. If we're going to go to the trouble of writing something to publish events, even if it's just for testing, then we might as well write something to publish events and have a suite that knows how to publish and consume events as a part of a kind of open source toolkit for doing this kind of thing. So that's something that we're going to do, and something I alluded to at the start, we're going to do feed owner alerting. So Feed Facade will have the ability to say to somebody, either on Google Talk or an instant messenger thing, or maybe an SMS message, we're getting 404s from your feed, or we think your SSL certificates have expired, can you please sort it? I'd like to be able to extend that to say things like, your polygon doesn't start at the same point it finishes at, it's broken, your polygon crosses itself, please fix it. Possibly even warnings, your polygon contains a high number of vertices, it's going to slow down processing. Perhaps you could think about normalizing or simplifying a little bit. So that's something that I think, actually that last one of improving the feedback loop probably is top of my list for interesting things that we might do. That is the end of what I was going to talk about, and I was hoping to do Q&As. If you're watching this video, maybe I'm on chat, but I'd be really happy for Elliot to collect your questions, and I will feed back to you as soon as I possibly can. Rewind. The front page, that's my email address. You should feel very free to email me. That's my Twitter handle, Ian Ibbo. That's a Google Talk address. If you'd like to chat me on Google Talk instead, please feel free. And I'm really happy to listen to your feedback. The intention here is to have something that's open source and have a community. So by all means, get the source code, tell me it's rubbish, tell me how to improve it. Really happy to have your feedback. Thank you very much for sticking with me and listening to me monologue. I hope you're having a great conference, and I'd like to talk to you all soon. Bye-bye.